Hello everybody, in today's video I am going to be talking about the importance of 3D design in aerospace engineering. From the Wright brothers' groundbreaking first flight to the recent Indian Space Research Organization's lunar mission, our determined pursuit of space exploration continues to push the boundaries of what science can accomplish. We have sent people to the moon, launched satellites to collect data from billions of kilometers away, and are even trying to make space tourism a reality. But have you ever wondered what goes into making these incredible aerospace missions possible? Unsurprisingly, a vast knowledge of science and engineering is required, but did you know that 3D digital design is a critical tool used by aerospace engineers? From early planning to the construction stage, digital design is an immensely useful tool for the precise craftsmanship necessary to guarantee the seamless launch and journey of these intricate space probes. In this video, I will be talking about why 3D digital design is so important to the field of aerospace engineering. As I wanted to combine my interest in design with my passion for space, I ended up building a 3D model of a rocket. I'll be using this model to demonstrate how digital design is used in making all of the fascinating devices that explore space. 3D digital design is used in four main stages during the building of a space probe: visualization, prototyping, testing, and simulating. There are many types of 3D digital design tools, but CAD or computer-aided design is the main one. Let's start with visualization. In aerospace engineering, 3D visualization is the creation of detailed, three-dimensional representation of space probes or related components using specialized software and technology. For a second, imagine trying to build a complex puzzle but without ever seeing the picture on the box. 3D visualization is that picture on the box for aerospace engineers, as it allows engineers to enhance their understanding of the space probe that they are trying to build. A 2D sketch does help in conveying a basic idea, but drawings do not depict how a component will fit together. With 3D visualization, engineers are able to get a 360-degree view of what they are going to build. As one can imagine, these devices involve exceptionally technical calculations to design and millions of dollars to get the material to create them. There is no room for error when dealing with such intricate yet massive probes which come with a hefty price. This is why visualization is a paramount for scientists, as it is the most accurate depiction of a probe that they can use without any physical materials. Since the space in 3D design is infinite and can be edited at the click of a button, this is also the stage where engineers can make improvements. This helps in saving precious time and resources and allows scientists to test their creativity while also remaining technical, as digital design has the capabilities to allow for accurate measurements. Next, we have prototyping. Prototyping is one of the most important uses of 3D digital design in aerospace. In simple terms, prototyping involves creating digital models or prototypes to validate and refine design concepts before actual construction, ensuring they meet safety and performance standards. These prototypes are usually made from 3D printing certain parts. This way of confirming the model is comparatively affordable, allowing engineers to make changes faster while saving resources. For example, the nozzle is a part of a rocket that directs and accelerates the expelled exhaust gases to generate thrust and propel the rocket. Suppose an engineer wants to try another design of this nozzle. The engineer can design one using CAD and then using it test how it will react in different scenarios like weather conditions or in low atmospheric conditions like the troposphere. This method can help them in risk reduction, which is basically reducing the risk of failure during the journey of a space probe. Identifying and addressing potential issues in the digital models, aerospace projects can avoid costly errors and delays during actual construction and testing. In addition to risk reduction, 3D digital prototyping also accelerates the innovation process, enabling engineers to explore new design possibilities and refine their concepts with greater agility and cost efficiency. This iterative approach fosters progress and creativity in aerospace technology. Prototyping leads us to our next factors: testing and simulating. Testing involves assessing aircraft, spacecraft, or components to make sure they meet design specifications and operational requirements. Simulating, on the other hand, refers to the assessment of an aircraft in certain environments. According to NASA's technical reports, they have simulations which are realistic to Earth's atmosphere and how they would affect a rocket, and that's what they use to test exit or re-entry conditions on a rocket. Testing and simulating go in hand as they both are specifically to check if a rocket can withstand everything. During tests and simulations, 3D digital design is extremely important, as these simulations are made from 3D design softwares as well as real-life simulations. These digital models serve as the foundation for simulated testing, enabling engineers to analyze and predict performance of an aircraft, spacecraft, or components under various conditions, such as different flight scenarios or extreme environments. Let's recap the benefits of using 3D design in aerospace engineering. We have cost-effective prototyping, enhanced visualization, error detection, rapid iteration of ideas, risk mitigation, efficient testing, and realistic simulations. Now I'd like to present a model of the GSLV Mach 3 that I've created. I decided to make my own rocket for multiple reasons, primarily to gain first-hand experience and step into the shoes of an aerospace engineer. I also wanted to demonstrate the significance of 3D design in aerospace through practical exploration, whilst also refining my own digital design skills. Through this model, we can see the five main stages of the rocket: the payload stage, the upper stage, the interstage, the booster stage, and the core stage. All of these five stages have had different designs in the past. As we can see in the GSLV Mach 2, the upper stage was much smaller than in the GSLV Mach 3. This is because in the GSLV Mach 2 there were many shortcomings due to the size, and one of the main reasons this rocket failed is because of a gas leak in the upper stage. In addition to addressing this gas leak problem, the GSLV Mach 3 design also includes a number of other changes that are intended to improve the performance and versatility of the rocket. For example, the GSLV Mach 3 has a larger upper stage and a more powerful cryogenic engine. This gives the rocket more thrust and allows it to carry heavier payloads into higher orbits. Notably, these improvements were done with the help of 3D digital design, as engineers were able to visualize and test new and better designs in a cost-effective way. Most engineers use high-end software to make models of their space probes, but I decided to use Blender to make my model as I have prior experience with Blender as well. Blender is a 3D graphic software. To make this model, I used a method that I like to call tracing. I put a photo of the rocket behind my meshes, then basically traced through the rocket to make the base of my rocket. This was extremely helpful in getting the right shape for the rocket and then work on the details afterwards. But whilst making the rocket, I also faced a lot of challenges, which was mostly with curved surfaces. As a beginner in Blender, I was not able to make smooth curved surfaces that followed the outline of the rocket. To overcome this, I used the UV sphere to try and make the best and smoothest curved surfaces. The UV sphere is a mesh in Blender with the most vertices. This makes it the best mesh to use for curved surfaces. Another problem that I faced was accuracy and precision, as it was hard to convert exact dimensions of the rocket onto the Blender meshes. This made the quality of my design low. The reason for this is, Blender does not specialize in aerospace, making it not the best tool to create exact and accurate replicas of rockets. This brings me to the challenges of 3D digital design in aerospace. The first one is quality control. Quality control in 3D digital design is a demanding process, which focuses on ensuring the end product aligns with the specified standards. Meticulous attention is needed during 3D printing, as this technology can introduce defects like voids, delamination, and layer inconsistencies, which may jeopardize the structural integrity. Another disadvantage of 3D digital design is the speed, as these 3D designs need to be 3D printed. This 3D printing can be extremely slow, especially for large and complex parts, causing delays in the finished product. While I have mentioned cost reduction as a benefit of 3D digital design, it is still important to note that the equipment for 3D printing is exceptionally expensive, particularly for industry-grade machines. Before we conclude, I'd like to tell you how I used the two factors of 3D design in my model. Whilst making the model, I was able to visualize the different parts of it. And I also ended up 3D printing my model, making it a prototype of a rocket. I was not able to do any 3D testing or simulations, but still, I was able to explore visualization and prototyping myself. In conclusion, we've embarked on a journey today to explore the incredible importance of 3D design in aerospace engineering. From visualizing intricate spacecraft designs to ensuring their flawless performance through rigorous testing and simulation, we've seen how this technology revolutionizes the way we reach the stars. As we've delved into the world of aerospace engineering, one thing is clear: the future of aerospace exploration is innately tied to 3D design. It's a dynamic tool that empowers engineers to push the boundaries of possibility and reach new heights, quite literally. The GSLV Mach 3 model that I have created showcases the 3D design process. I found it so interesting that I was able to make my own model, albeit on a small scale, as even 15 years ago being able to do this on a home PC would have been unthinkable. But this process served as a reminder of how far we have come in the field of aerospace design and how much further we can go. It showcases the evolution of rocket design, underscoring the pivotal role that 3D digital design plays in refining and perfecting these marvels of engineering. As we conclude this video, I'd like to leave you with a quote from the great visionary and aerospace engineer Wernher von Braun. "Man will not always stay on Earth. The pursuit of light and space will lead him to penetrate the bounds of the atmosphere, timidly at first, but in the end to conquer the whole of solar space."